A big shout out. Thank you so much for our TikTok fam who's joining us in here as well. We're going to have a really awesome session. For those of us who are joining us on Zoom, if you know you've got friends who should be in this session, please drop them a message as usual. Remind them class has started. We're going to get going. We're going to cover a little bit of a difficult topic. I think today's topic is a topic that a lot of people generally find difficult. But as usual, with the learning space way, we're going to really try and make it make sense for you guys, make it a bit easier. What I want to ask for is ask for your patience today. So make sure you've got your formula sheets, make sure you've got a calculator. Acids and bases is also one of the more calculator heavy sections in chemistry, but I believe we're going to make our way there. Let's make sure we are all ready to get our groove on in the acids and bases world. Okay, let me get my board up and running. And then again, today technology is going to behave. It's not going to do what it does in our last session, and we're going to be able to easily see the screen all together. Let's see, 3, 2, 1. Yes, Theo, just confirm if you can see my screen.
I can see it.
Fantastic. Awesome, guys. Let's get going. Acids and bases, right? So acids and bases are quite important. So when we look at our types of reactions that we generally tend to do or come across in chemistry, right? Acids and bases are one of those. And acids and bases, really, if I can give you acids and bases in a nutshell, acids and bases is basically all about the transfer of protons. You'll see a topic you guys have coming later on now in term 3, you might already be on it, or it might still be coming, is electrochemistry, which is all about the transfer of electrons, right? And that's got redox reactions as its base. In this case, we're dealing with a transfer of protons. So as usual, I'm going to start today's session with just an overview that we normally take from the notes in our exam guide. I'm going to take you through the notes in our exam guide, step by step. What are the key things you need to know about that? And then again, remember, we are prepping for those prelims. So we're going to do some slightly difficult questions today. But again, the key thing is to get you guys as ready as possible to be able to nail this topic, right? So what I'm going to do, I'm going to switch my video off just to sort of save you guys some data for the rest of the session. You guys saw my face, and I'll put it back on towards the end of the session again as we kick off, right? So let's jump in. Acids and bases, right? So the first thing you'll always have to deal with, it's always question 7.1. They'll say to you, define an acid in terms of the Lowry-Bronsted model, or define a base in terms of the Lowry-Bronsted model. So let's look at that definition of acids and bases, right? So firstly, what we can see here is the fact that now we're going to have our Arrhenius theory and then our Lowry-Bronsted. I'm going to focus more on the Lowry-Bronsted because that's really the one that's still there in our ATP. In terms of our ATP, we don't really go through the Arrhenius model or the theory of acids and bases as much for CAPS. So I'll touch on that, but I won't even focus on it. I'll focus more on the Lowry-Bronsted. But again, our Arrhenius theory states that acids form H plus or H3O plus ions in water, right? So acids are substances that increase the concentration of H3O plus ions in water, and bases are substances that increase the concentration of OH minus ions in water. So we can see in our first reaction over here, HCl plus water will give us Cl minus and H3O plus. And we can see here that, again, we're increasing the concentration of H3O plus by adding HCl, which is an acid. So HCl is our Arrhenius acid. And then NaOH plus will give us Na plus OH minus. And you can see there again, NaOH is our Arrhenius base because it increased the concentration of OH minus. And in this particular case there, we've got NaOH in aqueous solution, right? Solution of what? What is our solvent? Water. So in water, it'll increase the concentration of OH minus. But the one that's more important that we look at our ATP and comes in there is the Lowry-Bronsted, right? So again, the Lowry-Bronsted model says acids are proton donors and bases are proton acceptors. So again, when we look at what is a proton, so we look there, protons, we're dealing with H plus ion, right? Why we call the H plus ion a proton? If you look at hydrogen, hydrogen only has one electron and one proton. Hydrogen doesn't have any neutrons. So if I remove the electron from hydrogen, all I'm left with is a single proton. There's no neutrons. That's why we refer to H plus as a proton, right? And again, in that case there, when you come back and you look at the definition, we can see HNO3 plus NaOH gives us NaNO3 and H2O, right? So again, HNO3, right, donates and gives away its H plus to become that NO3 there. right? And then NaOH, the OH minus accepts the H from the HNO3 and becomes H2O. So we can clearly see there that the HNO3 donated an H because it gave an H plus or donated a proton, it becomes our acid. And then NaOH basically accepted that OH and NaOH, it accepted the H plus, it accepted the proton, and therefore it becomes our Lowry-Bronsted base. Very important. 7.1, you'll always get a question like this. Let's quickly go down again, right? Between understanding ionization and dissociation. And the reason why I cover this is because sometimes you'll hear of people talking about strong versus weak acids or bases, right? Where they'll say something will, so an acid will ionize fully or ionize only partially, or a base will dissociate fully or only partially. So the reason why we use those two words, ionization and dissociation, they essentially mean roughly the same process as the process by which a compound will split up into its constituent atoms. But what's very important is how were those original atoms bonded. That's what makes a difference between ionization and dissociation. So in the case of ionization, right, we make ions for the very first time. It means in this case, HCl, right, was covalently bonded. Remember, with covalent bonding, we take substances that share their outer electrons. So that's very, very important. So with a covalent bond, when you separate them out, the one electron is going to now, for the first time, move from the one atom to the other atom. So in the case of HCl, hydrogen had its own electron when it was bonded with chlorine. But when they separate, that electron from hydrogen is going to move to chlorine, and that's why we end up with Cl minus and H plus. So we make ions for the first time, ionization. Whereas dissociation, the substance was ionically bonded to begin with, meaning they were already ions. How NaOH is formed is by taking Na ions, Na plus ions, and bonding them with OH minus ions. And then the electrostatic force between the two will bring them together. That's how you make NaOH. So when I split Na and OH, Na remains Na plus, and OH minus remains OH minus, right? No one gets new electrons that they didn't have before. Very important that we understand those two there. And once we've got a clear understanding of that, let's then go look at the difference between concentration, and then we'll touch on strength and weakness a little bit later. But then let's look at concentration as well, right? So again, with concentration, concentrated acid or concentrated solution, right, is one where a large amount of acid or base in proportion to the volume of water. So I've got a lot of moles per volume water or per volume of my solution, versus dilute, I've got a small amount of acid or base or moles of my substance, right, per volume of whatever my solute is going to be. So concentration just talks about how many parts I do have per volume. High concentration or concentrated is, many parts. Dilute is a small concentration, few parts per volume of my water. And then another critical thing to touch on again is the importance of understanding conjugate acid-base pairs, where, again, conjugate acid-base pairs differ by one proton only, right? And that proton is basically one that was either donated or one that was received on the other end. So an acid donates a proton to form its conjugate base. So let's have a look at the example on the right-hand side there. So HCl becomes Cl minus plus H plus. So if this is my original acid, the conjugate base is Cl minus, because HCl will give away the H. What is left of HCl is going to be the Cl minus. So the Cl minus is my conjugate base. And then again, a base will accept a proton to form its conjugate acid. So in this case here, we've got Cl minus, which is going to be our base. It's going to accept an H plus, and then it's going to become, in this case here, the conjugate acid that we are dealing with there. So here's a reaction, a full reaction now, right? On the right-hand side, so we've got, fictional reaction, say, as it will happen there. So we've got Cn minus plus H2O becomes HCN plus OH minus. So we can see that Cn minus is going to be what our base is, because what happens is that from Cn minus, it becomes HCN. It accepted an H from the water, right? And in this case now, HCN becomes our conjugate acid. So we label that our original base is B1, our conjugate acid is A1, right? Then you've got water, which acts as our acid in this case. And then the acid is going to give an H away, and you're left with OH minus, and we call that our conjugate base, that OH minus. Fantastic. Then I'm going to just move on again. Note the conjugate of a strong substance is weak, right? And the conjugate of a weak substance is strong. For example, HCl is a strong acid. Therefore, its conjugate base Cl minus is going to be a weak one, right? Very, very important for us to note there. And then I'm going to jump a little bit now into the autoionization of water. Now, in the autoionization of water, right, we have, let's say, H2O plus H2O giving us H3O plus OH minus. So remember again that water is what we call an ampholyte, right? An ampholyte is something that is amphiprotic, meaning it can act as both an acid or a base. So in this case here, right, for the autoionization of water, this reaction, one H2O molecule acts as an acid and the other one acts as a base. And as that happens, we then create H3O plus and OH minus. And now Kw is what we call the equilibrium constant, right? Of the autoionization of water. So the Kc value for that reaction, we call that Kw, Kw just generally, right? So just like Kc, Kw only changes with temperature. And Kw at 25 degrees Celsius will always be this value here, 1 times 10 to the negative 14, right? Very important that it must be at this temperature. If it's not at 25 degrees Celsius, it's not going to be that very same value. And we normally tend to use that quite a bit when we are dealing with acid-based calculations and pH calculations and concentration calculations with acids and bases, of which we're going to do very, very many today. So let's make sure we keep in touch of that calculation. Is going to become very, very critical and crucial for us today. Awesome. Right. Let me just check before I move on. Theo, are there any questions that I might be missing? Sorry, Theo, I don't know if you're there, but I'm assuming it's okay. Come again? Any questions?
No, they were saying your screen is blurry, but I think it's their network.
I can do a speed test on my side just to make sure, but it's probably their network on their side, because we're not on the road today, so at least got the pleasure and the privilege at this point. It's not even a pleasure; it's a privilege truly of having good internet connectivity. So they may just double check their connection, maybe move around to a spot with slightly better network. It'll help your screen become not so blurry. But either way, for the guys who are with us on Zoom, you guys should all have these books anyway. So you should have this book with these notes in it. So just use your book for this lesson, and then it'll help you for this part. And then where you'll need the screen again is when I come to do the problems, right? Awesome. Okay. Sweet. Now we are going to have a look at indicators, right? So indicators are when we need to be doing and dealing with things like titrations, right? So with indicators and titrations, there's 2 key terms we need to learn. They sometimes ask these as well as a theory question, right? Where they'll ask us, what is the equivalence point, or what is the end point of a titration? This is very important to note. So the equivalence point of a titration is where all the acid or the base has reacted. Sorry, Theo.
Maseko is asking which book.
Maseko it's the book that he is still to get, but everyone else in the Zoom call should have the book. Yeah.
Okay.
Cool. Sweet. So again, indicators. So the equivalence point of a titration is the point where all the acid slash base has reacted with all the base slash acid, right? So when all my acid has reacted with all my base, that is what we call the equivalence point of a titration. But then the end point of a titration is when the indicator changes color. So depending on which indicator you've got, it will then change color from one to the other. And we're going to have a look at some of the indicators we can use. Sometimes they'll give you a question of, please select the right indicator for the following titration. And you need to be able to figure out, well, how do I then know from that point onwards? And we'll have a look at that as well, right? So For titration to be accurate, the equivalence point and the end point must happen at the same time. That's how you know that you have a really accurate titration, right? The salt formed will change the pH of the solution at the equivalence point, right? So we will have a look at hydrolysis of salts just now. And thus, an appropriate indicator must be chosen to take this into account. For example, if a base 6 salt is formed, an indicator that changes color in a basic range is required, right? Very, very important, because some people think that indicators will change color at 7 always. That's not always the case. So it depends what we're dealing with. So we can have an indicator that works for a low pH range when I'm expecting an acidic endpoint, or a neutral endpoint, right? When I'm expecting a neutral endpoint, so somewhere around 7, which is a mid pH range, or we've got one for a higher pH range where I'm expecting a slightly more acidic endpoint, right? Because if I think about this, strong acid and a weak base will give me something that's going to be more acidic, right? Because that weak base is not going to cancel out all of that acid immediately. So I'm going to end up something with a bit more of an acidic, lower pH. So something like methyl orange is going to be a better indicator to use, because my endpoint and my equivalence point will probably happen at the lower pH ranges. In that case there, methyl orange is going to then have a color change of red into orange into yellow, right? Where basically on the lower end of the range is going to be more red. In the middle of that range is going to be orange, and upper part of that range and above is going to be yellow. Then if I know I'm dealing with something that's going to be more of a neutral solution when I'm done, you're looking at something like bromothiamyl blue, right? Bromothiamyl blue goes from yellow, turns into green, and then ends up in blue on the upper end. So if it's still a bit more acidic, it's going to be yellow. If it's going to be a little bit in the middle, it's going to be green closer to 7, and above that, it's going to be blue. So if you know you're dealing with strong acid, strong base, or weak acid, weak base, you're going to be looking at using bromothiamyl blue as the indicator for your reaction. And then lastly, the one that is very difficult to say, some people say phenolphthalein, I say phenolphthalein. It doesn't really matter as long as you can write it down in the exam, right? They're not going to be listening to how you pronounce it. So that one is when you're looking for more of a basic endpoint, meaning I'm going to be dealing with a strong base and a weak acid. I expect my endpoint or my equivalence point to be north of 7, sort of slightly higher up in my pH ranges. And that one basically goes from colorless and it changes to pink as your pH range goes up. And that you're looking in a pH range of 8.3 to 10, which is going to be where your equivalence or your endpoint is going to sit, right? That's how we can basically deal with some of those ones there. And now what I want to also do, again, come back and let's look at that relative strengths of acids and bases. So remember again, what I said is a strong acid or a strong base is one that will ionize or dissociate completely in water, right? So if you look at a strong acid, it will ionize completely or near completely in water to form a high concentration of H3O plus ions. So if you look at the reaction we've got there, H2SO4 plus water, right? Like almost all of this, or almost all of our H2SO4 is going to react to create lots of our product, right? So if you think about like how we were dealing with Kc last time, we've got what we call Ka and Kb, the equilibrium constant for acids and equilibrium constant for bases. So when you're dealing with now a strong acid is going to have a very high Ka value because I've got lots of products, very little reactants. But a weak acid is going to have a very low Ka value, or a Kc for acids, right? So again, a weak acid will ionize incompletely or only partially in water to form a low concentration of H3O plus ions. So I'm going to have a very low Kc value for that ionization reaction in that particular case, or a low Ka value. Then for bases, similar story, right? A strong base is going to dissociate completely or nearly completely in water to form a high concentration of OH minus ions in water, very high Kb value. Or I'm going to then have a weak base, which will then dissociate or ionize, incompletely, only partially in water to form a low concentration of OH minus. I'm going to have a very low Kc or Kb value for this one there. All right, now let's look at some common acids and bases, right? It's very good to always know what are some of your strong acids, what are some of your strong bases, and to be able to just memorize these ones, because usually they'll ask you some of these things when you're doing these questions. So in terms of strong acids, So we've got nitric acid, HNO3, hydrochloric acid, HCl, sulfuric acid, H2SO4, some strong bases, so NaOH, KOH. A little cheat sheet I told you guys the last time we had a lesson is if you want to find what can be referred to as a strong base, just take a group 1 metal with an OH. So potassium hydroxide, sodium hydroxide, etc. Those will give you strong bases, right? And then your weak bases, you're dealing with ethanoic acid. That's, the acid you find in vinegar or lemons. You've got oxalic acid. You've got carbonic acid. Those are some weak acids. Weak bases, you've got ammonia, you've got potassium carbonate, you've got calcium carbonate, and sodium hydrogen carbonate as well are some weak bases. Very important that you have these. These will be able to help you, right? Okay, then again, types of acids that we are dealing with there, we've got monoprotic, diprotic, triprotic, and polyprotic acids, right? So in this case here, a monoprotic acid is an acid, right, where it only has 1 proton to donate. So something like HCl only has 1 H to give. HNO3 only has 1 H to give. CH3COOH, right? Our ethanoic acid only has 1 H to give. Don't make the mistake and think ethanoic acid is a polyprotic acid, because the CH3, right? The CH3 that we find here, this H3 is not going to be donated anywhere. The H that is donated is going to be this H over there. That is the acid that is going to be donated, the H that's going to be donated. Then a diprotic acid is going to be an acid that's got 2 H's to give. So H2SO4, sulfuric acid, oxalic acid has got 2 hydrogens to give. Triprotic acids are going to be things like H3PO4, right? Phosphoric acid, where it's got 3 hydrogens to give away in that case there. And polyprotic acid is anything with more than 1 proton to donate. So a diprotic and a triprotic acid are all examples of polyprotic acids. Very, very important. Okay, and then now, not lastly, but second lastly, let's look at our acid-base reactions. These are reactions that you should know, right? The first one that we always start off with is an acid plus a base will give you salt and water. But there's other acid-base reactions that we need to then be able to look at as well and understand. We need to know, given something reacting with something else, what are the products going to be? Sometimes in a question, they will give you something like that, where you must then determine what the products are going to be, right? So let's look at this one now. So if we have an acid plus a metal, right? So a metal means just like a magnesium, silver, gold, anything like that, will give us salt and hydrogen gas. Very, very important. So when I say salt, I don't mean NaCl, not table salt, but I mean salt as in an ionic compound, right? That's ionically bonded together. So we've got our acid, which is going to be in this case our HCl. Our metal is going to be magnesium. Our salt will then be magnesium chloride plus hydrogen gas. That's how it's going to be. Another one is going to be an example is going to be acid plus metal oxide will give us salt and water. So in this case, our acid there, H2SO4, we're dealing with our sulfuric acid, right? Metal oxide, we've got mercury oxide, and that mercury oxide is going to then react with the acid to give us salt and water. So the salt is going to be mercury sulfate and water in that case there, right? And then acid plus metal hydroxide will give us salt and water. So acid plus metal hydroxide, our acid is what? Nitric acid. Metal hydroxide is going to be sodium hydroxide. And that will then give us sodium nitrate plus water. That's our salt and that's our water. Finally, acid plus metal carbonate will give us salt, water, and carbon dioxide gas. So there we've got our acid, which is going to be ethanoic acid, plus our metal carbonate is going to be potassium carbonate. That will then give us there our CH3COOK plus water plus carbon dioxide. An easy way to remember this, acid plus base will give you salt and water, right? Now, if whatever my acid is reacting with has got an oxygen, I'll get salt and water, right? If it doesn't have an oxygen, I'm only going to get salt and hydrogen. If it's got oxygen and it's got carbon, I'm going to get salt, water, and carbon dioxide. So acid and base, you'll see, I always end up with salt and water. Acid, metal oxide, because this has got oxygen, I get salt and water. That has got oxygen, salt, and water, right? The carbonate is going to have carbon dioxide and oxygen. So I'm going to get my water from the oxygen, and I'll get the carbon dioxide from the carbon that exists there. And then here, metal and acid, there's no oxygen here, so I'm only going to be able to produce hydrogen gas, because if I had oxygen, I'd be able to create water, which in this case I can't. All right. And then we've got, finally, before we start our questions, the hydrolysis of salt solutions, right? So the hydrolysis of salt solutions, what this means. So in a neutralization reaction, right? Like, for example, if we're doing a titration, right? One of the products is always going to be a salt. You saw when we were doing acid-base reactions, you always have salt as one of your products, so, right? So sometimes that salt is going to react again with water, and this is going to change the pH of my solution. So the salt that comes out will react again sometimes with water. It'll change the pH of my solution. So again, let's look at the key principle here. The iron, right, from a strong substance is going to be weak, i.e. it doesn't easily react with water again. And the iron from a weak substance is going to be strong, meaning it will easily react with water again. Remember, we mentioned this earlier when we were looking at our problems there, right? That the conjugate of a strong substance is going to be weak. The conjugate of a weak substance is going to be strong. This is what we were dealing with there. The application of that now is where we are looking at our hydrolysis of salt solutions in this case here. So let's have a look now at this hydrolysis of salt solutions and how this then basically works out, right? So remember what I said to you. To keep it simple, before we go through all the hectic theory, to figure out whether you're going to have a acidic salt, basic salt, neutral salt, if I'm going to make this super simple for you, strong plus strong, neutral. Weak plus weak, neutral. If it's strong plus weak, you're going to take the form of whatever was strongest. So strong acid, weak base, acidic. Strong base, weak acid, I'm going to be basic, right? And then in detail here, it's going to be, but remember the simple version I gave you just now. So let's look at the detailed one. A strong acid plus a weak base is going to really give me an acidic salt, because again, remember I said, whichever one is stronger, that's going to take precedence, right? So you know that the pH is going to drop below 7. So you have, for example, ammonium nitrate, right? So the ammonium comes from a weak base, which is ammonia, and that's going to then react with the water, right? And then the nitrate, which comes from a strong acid, which is HNO3, that won't react, because if it comes from a strong acid, the conjugate is going to be very weak. It won't react with water, meaning eventually when you hydrolyze that salt, right, you're going to take ammonium nitrate. Ammonium and nitrate are going to split up. Only the nitrate is going to react with water again to form ammonia and H3O plus there, right? Okay. And then that H3O plus that we're dealing with there is what's going to then result in me having an acidic salt, because that concentration of H3O plus in water really determines what my pH becomes, right? Then again, weak and strong, looking at a weak acid and a strong base, we're going to end up with a basic salt, right? Practically how that happens. So we're going to have, let's look at this right now. I call this chacuna just because it's CH3COONA, right? So the chacuna salt, we're going to have the chacu part of the salt break off, right? So again, the chacu part of the salt comes from a very weak acid, right? It comes from acetic acid. And because it's going to be from a weak acid, the conjugate is going to be strong, which means it'll react with water. And then you're going to end up with this part of the reaction here. The Na comes from a strong base, from sodium hydroxide. So, right, the strong base is going to have a weak conjugate, which means the conjugate will not react with water. So basically all that happens is that the sodium will stay in solution, but my chacu is going to then react with water again. And then what you see there is you have your chacu plus your water giving you acetic acid plus OH minus. And this OH minus is what's going to then result in my pH increasing and becoming more basic. And then finally, let's look at strong versus strong, like I mentioned. Again, my sodium comes from sodium hydroxide. That's going to mean I end up with a weak conjugate, will not react. My chlorine is going to come from a strong acid. That's HCl. The conjugate will be weak, will not react, right, at the end of the day. So we end up with a neutral salt, because that is not going to react with the water again. Again, just to summarize this part before I make it seem too complicated: strong acid, strong base, neutral salt. Weak acid, weak base, neutral salt. Strong acid, weak base, acidic salt. Strong base, weak acid, basic salt. If that's all you remember, that's all you need right now for this particular thing. The detail is not that important for the purposes of application of what we need to do. Fantastic. Now we're going to jump straight into our questions. And again, remember, guys, I'm going to remind you guys, again, like I said, it's going to be a little bit of a tough one today, right? But not tough. Let me change my words. It's going to be challenging. And I think we are all up for a challenge because everyone in this session is going to be someone who's really up for a challenge. So we're going to start off with some multiple choice questions as usual, just to get you guys warmed up, right? And to get a little bit of interaction going. So let's look at the first question in multiple choice. It says the following: nitric acid, which is HNO3, and ethanoic acid, CH3COOH, of equal volumes and concentrations are compared. Now consider the following statements regarding these solutions. Statement number one says they have different pH values. That's statement number one. Statement number two says they both have the same electrical conductivity. That's statement number two. Statement number three then says both solutions require the same number of moles of potassium hydroxide for a complete neutralization. All right. Now, the question that I'm going to ask you guys today is which of the above statements is or are true? Is it A, only one, B, 1 and 2 only, C, 1 and 3 only, or D, 2 and 3 only? Have a look at that. Think about it now. I want you guys to post your answers in the chat. If you're on TikTok and you just joined us, we've got a question up on the screen that I want you guys to answer. You're going to answer this question simply by posting your answer A, B, C, or D in the chat. I'll give you guys about 5 minutes to have a think about it, and then let's see how well you guys can do with this one. All right. Remember, I said acids and bases is a little bit of a tricky topic, but today we're going to try our very best to make sure you guys are able to get a very strong handle on this topic. I'm giving you guys 5 minutes to try this question. Thank you for those already throwing their answers in. I appreciate it. Okay, getting a nice number of answers coming in. Fantastic, guys. It's looking good. Looking really good. Let's see how you guys do. I'll give you guys 60 more seconds, and then we'll look at the answers together. Okay, a little hint for those that haven't given us their answers yet. Think about what is the difference between the two substances that have been given. What is the difference between nitric acid and ethanoic acid? What is that difference? And that might help you be able to answer the question. Okay, you got 45 seconds left. Okay, 10 seconds to go, and then we're going to have a look at the answer. 5, 4, 3, 2, and 1. Awesome, guys. Let's have a look at the answer for this particular question and to see how we really can go about finding this solution, right? So the key thing there is to look at the information given. So first of all, we need to notice that nitric acid is going to be one of our strong acids, as we saw earlier on. And then ethanoic acid was one of our weak acids, right? So to remember, strong acids ionize completely or near completely. Weak acids ionize only partially, right? So let's then analyze our questions one by one, and then we'll be able to determine what's going to really work for us. So number one, It says the following statements. Number 1 and number 2 have different pH values. And that is true, right? Because of the fact that if one is strong and one is weak, a strong acid is going to have a pH, that's going to be much lower than a weak acid. Weak acid is going to be closer to 7. A strong acid is going to be closer to 1. So yes, that is true. They do have different pH values. Number 2 says they both have the same electrical conductivity. And at that point, I would say, actually, no, they don't, right? Because they don't ionize or dissociate to the same level, they don't ionize to the same level, they won't have the same electrical conductivity because they won't have the same number of ions in solution, right? HNO3 is going to ionize completely, which means it's going to have a lot more ions in solution than acetic acid. Acetic acid will only have a very few ions in solution because it ionizes only partially, meaning, nope, they don't both have the same electric conductivity. HNO3, the stronger acid, is going to have much higher electrical conductivity than our weak acid because it will ionize more completely and have more ions in solution, which is what we need to transfer charge. All right. Then number 3, both solutions require the same number of moles of KOH for complete neutralization. And again, that is not going to be the case, right? Sorry, apologies. Both solutions require the same number of moles of potassium hydroxide for complete neutralization. Sorry, that is true. That is true. Reason why it's going to be true, right, is when we look at the types of acids, we're dealing with a monoprotic acid for HNO3 and a monoprotic acid for acetic acid, which means, yes, they'll require the same number of moles of KOH because it's down to the number of hydrogens that you put out to determine how you're going to then be neutralized, which means in this case, what we will find is that statement 1 is true, statement 2 is not, and statement 3 is true, which means eventually what we're going to then deal with here is that C becomes our correct answer, that only 1 and 3 are true. If you got that right, give yourselves a round of applause. Well done, guys. I really appreciate you. And if you didn't get it right, don't stress, don't worry. There's another question coming up. You can redeem yourself with the very next question. Okay, I'm going to move on to the next question if we are all happy to do so. And the next question looks as follows. I need to zoom out a little bit just because there's a lot of information on the screen. And there's the question there, right? It says, I'll read the question out for you. It says the apparatus in the diagram below is used for the titration between HCl, hydrochloric acid, and KOH, potassium hydroxide, right? So we can see there in our titration mixture at the bottom, HCl is being dropped into our titration mixture. Now it says, in a titration, the learner accidentally exceeds the endpoint, right? Which one of the following will be true for the titration mixture? A, the concentration of H plus ions will be greater than that of the OH minus ions, and the pH will be less than 7. Or B, my concentration of OH minus ions will be greater than that of the H plus ions, and the pH will be less than 7. Or C, OH minus greater than H plus, pH greater than 7. Or D, H plus greater than OH minus and the pH greater than 7. This is one that's going to be fairly quick. I'll give you guys 2 minutes to try and answer this one. Remember, if you've just joined us on TikTok, just look at the question and then whichever answer you believe is the correct answer, put A, B, C, or D in the chat. Fantastic, guys. I'll give you guys 2 minutes to quickly do this one. Just simply put A, B, C, or D as your answer in the chat. Okay, thanks. On TikTok, we see some answers are coming in there. Thank you so much, guys. And the guys on Zoom as well, there's answers coming in. Thank you so much. I appreciate it. There we go. We got lots of answers coming in. That's fantastic. Thank you guys so much. Okay, I'm going to give you guys 30 more seconds. Come on, team TikTok. We need more answers out of you guys. So just post an answer A, B, C, or D in the chat. Just paste whatever you think the answer is in the chat. Okay, 10 seconds, guys. 5, 4, 3, 2. Thanks, Leander. 1. And time is up. Awesome. Let's have a look at this one. I've got a mixture of answers. I've got some A's there in TikTok, on Zoom. I've got some A's. I've got a D. I've got a B. I've got a lot of A's, another D. Okay, I've got a bunch of answers, but predominantly I'm getting the answer A. Let's see if you guys are correct, right? So let's see what happens. So at this point here, right, we're dealing with potassium hydroxide and HCl. So that's a strong base and a strong acid, right? We expect our endpoint to be somewhere very neutral because it's strong and strong. So somewhere very neutral is the endpoint. That's where it's supposed to be, all right? Okay, now the person goes beyond the endpoint. And remember, we're starting off with our mixture being mainly basic and we're adding the acid, which means we're starting on the higher end of the pH scale, right? Above 7, and we're coming down pH, trying to get close to our 7 mark in this particular case there. So if I go past my endpoint, it means I'm going to go past 7 and go slightly below that, right? So already I expect my pH for this thing to be less than 7. And if my pH is less than 7, I can already scratch out 2 of the answers that I know are not going to be, because it's not going to be C, it's not going to be D. Okay, so anyone who put D, that wasn't the correct answer, but don't fret. We're going to see which is the correct answer right now. Remember, guys, I love answers that might be incorrect because number one, they do 2 things. Number one, it allows you to fix a misconception that you have. I always say, rather get something wrong in a lesson, don't get it wrong in an exam. So if you get it wrong in the lesson, we have time to correct you. And then when you get to the exam, you will get it correct. And usually if you get it wrong in the lesson, it's fine. Don't panic. This is where we're here. It's called the learning space for a reason. We're here to learn. We're not here to be always correct. We're here to learn in the process, right? Cool. Let's look at what we've got left. We've got A and B left. So the pH will be less than 7. Now, which is going to have the higher concentration, the H plus ions or the OH minus ions, right? If you think about, again, with our acids, as we add more acids, we're increasing the concentration of H3O plus or even H plus ions in solution. If we're adding more base, we are increasing the concentration of OH minus ions in solution. So in this case, we're adding acids, and we even went past the endpoint, right, where the concentrations might have been equal. And in this case, we're going to have more H plus ions rather than OH minus ions. So B will not be the correct answer. If your answer was A, give yourselves a round of applause. Well done for that. A is the correct answer for this particular problem. Well done, guys, for that. I appreciate all of your inputs. I appreciate your interaction in this session. The more you interact, the more useful this lesson becomes for you, right? If you just sit back and you become a spectator, you don't learn as much from the session. So it's very important that you do interact, and I appreciate you guys for that. Awesome. That was now the first little interactive Q&A for us. What I'm going to do is we're going to jump into now a more structured question. Now that we've warmed ourselves up, we're ready for the game time, right? Because we now are going to go into a lot of the calculation-based work, right? Okay, if everyone's ready, I'm going to jump straight in. I don't see any questions on TikTok. I don't see any questions on Zoom. I assume everyone is happy. Zoom team, if you guys are happy, give me a thumbs up if you're happy for me to continue. Just give me a thumbs up in the chat or in your reactions. Even on TikTok, if you're happy for me to continue, just put a thumbs up in the chat so I know that you guys are happy for me to continue. Okay, fantastic. I'm getting all the thumbs up. I really appreciate it. Thank you for those that have just joined us on TikTok. We are about to start another question on acids and bases, right? Awesome. So let's look at this question right here. And again, don't panic, don't fret, guys. This is not as difficult a topic as you might think it is. We take it step by step. And when you go with it step by step, I'm going to show you a method today where you really plan your journey as to how you're going to solve this problem. And once you've done that, you'll see it kind of goes well. All right, so let's look at question 7. Question 7 says, to identify metal M, right? So metal M is an unknown metal carbonate. Metal M in an unknown carbonate, metal carbonate, MCO3. The following procedure is carried out. So there's one step, and then there's going to be step number 2. Step number 1, 0.198 grams of impure, that, let me quickly just make a little note. That's going to be useful to me. So 0.198 grams of impure M carbonate is reacted with 25 cubic centimeters. Let me maybe pick a different color for that. 25 cubic centimeters of a 0.4 mole per decimeter cubed nitric acid solution, right? So I'm reacting this metal carbonate with a particular acid. Before I move on, let's quickly see. Remember when we were doing at the very beginning of the lesson, our acid-base reactions. So when I mix a metal, if I mix an acid with a metal carbonate, what are my 3 products, right? Don't give me the specific names of these products. You're going to give it to me in generic terms. So if I said acid plus metal carbonate, what are my 3 products that I'm expecting? Please post your answers in the chat. Remember, we've got acid plus base equals salt and water. We've got acid plus metal gives us salt and hydrogen. What do we get if we react an acid with a metal carbonate? What are our 3 products? We've got 3 products. If you remember all 3, post all 3. If you remember only 1 or 2, post only 1 or 2. Debucho, thank you so much. You've thrown in one there. Someone also on TikTok, thank you guys for your answers. You guys are doing really well, right? So if you have a metal carbonate plus an acid, you end up with salt, water, and carbon dioxide. Very, very, very important, right? And we can clearly see that. If you come back and look at our reaction, we've got acid plus metal carbonate giving us salt, water, and carbon dioxide. You see where these things become a little bit necessary. Sometimes they'll give you a question and they won't give you the products, right? They'll just say, this reacts with this. And you need to be able to determine what those products are if it's going to be a slightly higher order question, right? But we're going to get there. Someone on TikTok said this topic is difficult. It's not difficult. It's challenging. And we're always up for a challenge, right? So let's look at this. So that's step 1. We mix our metal carbonate with nitric acid. We get a salt, carbon dioxide, and water. Step 2, then the excess HNO3 is then neutralized with 20 cubic centimeters. Let me quickly make a note of that in a different color as something that we need to note. 20 cubic centimeters of 0.15 mole per decimeter cubed barium hydroxide, right? So what that means is that I'm going to start off with our initial reaction. Whatever did not react, right, of my HNO3 is going to be used in the second reaction. So here, what did not react is going to be used in my second reaction. I hope that makes sense to everyone. So I'm going to take HNO3, right? It's going to be in excess. My metal carbonate is going to be the limiting reagent for that reaction. My HNO3 will be in excess. Some of it will react with the metal carbonate until it's done. What remains is going to then be reacted with our barium hydroxide to then create our barium nitrate plus water. Okay, hope that makes sense to everyone. That's the 2 steps we're going to take. And it's very important that we pick up those 2 steps, because as we go through, they're going to ask us to solve 1 and 2, and we need to use both reactions as we go. So I'll take you guys step by step through it. Don't panic. If you feel like I need to just pause and clarify something, please post in the chat or put a hand up if you're on Zoom, and then I'll pause and clarify. So let's answer the first question, 7.1. I told you guys when we were doing our theory, right? They'll say, define the term strong base, or they'll say define Arrhenius base or Lowry-Bronsted base. So in this case here, they said define the term strong base. So again, remember, a strong base is one that ionizes completely in water, or ionizes nearly completely in water. So strong base, let me quickly, I'll just write it in here quickly. It's a base that ionizes completely in water. Excuse my spelling if I spell something wrong. I'm good at maths and science. I'm not good at English and spelling, but we'll get it through as long as you get the point, right? Okay, so it ionizes completely in water. And then it also creates a higher concentration of H3O plus or H3O minus. But if you got that, you should get the marks for that particular question, right? Right. Then let's jump to 7.2. 7.2 says, calculate, let me just move it up so we've got more space to work. Calculate the number of moles of barium hydroxide that reacted with the excess HNO3. Okay, so that is not going to be too bad because we were told that the excess HNO3, so if we come back and look at this step here, step 2, the excess HNO3 is then neutralized with 20 cubic centimeters of 0.15 mole per decimeter cubed barium hydroxide. So we've got what they gave us there is they gave us the volume and the concentration of our barium hydroxide solution. We can then just go find the number of moles, which is not too bad, right? Remember again, how do we do that? N is equal to C times V because concentration is number of moles over volume, right? Sorry, Theo, just confirm if you can see my screen. It said the screen share was paused for a second.
I can.
Oh, okay, that's fine. Okay. So number of moles of barium hydroxide that reacted with excess HNO3. So N is equal to C times V, right? And then when we do that, we can substitute the values in. The concentration was given to us as 0.15 moles per decimeter cubed. So that's going to become 0.15. The volume was given to us as 20 cubic centimeters. Remember, we're dealing with moles per decimeter cubed. So our volume has got to be in decimeters. So we have to convert that into decimeters. And then to convert from cubic centimeters to cubic decimeters, we divide by 1,000. So we can then say 20 divided by 1,000. And you can plug that in your calculator and you guys can give me the answer. Please and just post your answer in that particular case there. Sorry, someone noted something. They made a note there in the question. So sorry, I see that right there. It's a strong base, not an acid, so it's going to dissociate. Thank you very much for that. Thank you for picking that up. Awesome. Thank you for the answers you guys are putting down. And that is correct. So our final answer there should be 0.003 moles. Fantastic. If you got that right, give yourselves a round of applause. You're already a few steps closer to finishing this thing off, right? So in this case here, this question I think was out of, I'll tell you now. It's out of 18 marks, right? So far, you've got, the first one is going to be 2, the next one's going to be 3. You've got a clean 5 out of 18. It's not bad, right? So let's just keep going and see how far we can get with this question, right? Then they ask, what is the pH of the solution after step 1, right? This is where we now need to start really trying to figure out how is this really going to work. And this is the methodology I said I wanted to show you guys today. When they ask us, what is the pH of the solution after step 1? I'm going to just move this question up so we've got a bit more space to work. So we're going to then do a method where I like to then put my plan ahead. Before I start doing any calculations, I put my plan ahead. So I say, well, okay, to calculate pH, what do I need? So first of all, I know pH is equal to, negative log, right, of the concentration of H3O plus ions. Okay, so in this case there, I need the concentration of H3O plus ions, right? Let's look at step 1. I wasn't given that at all, right? So how do I basically go and look at that? So that's not bad. So what I need to just think about as well, how can I find the concentration of the H3O plus ions, right? And for me, what's going to become easy is you can then use basically the concentration of our HNO3 that reacted, right? Use that, and that will be able to tell you what the concentration of H3O plus in water is going to be. Very, very important, right? So I'm going to start by saying, well, I've got H3O plus. I need to figure out what that is going to be. So I'm going to use the HNO3. So I'm going to use this here to figure out, because that's my acid, right? That's what creates the concentration of H3O plus in my water. So once I've used that, that's what's going to basically be what I'm going to use in this particular case there. So 2.7.2.2, the pH of the solution after step 1. We are going to then first step, let's try and figure that one out. And then if I use that, the next step is to figure out the H3O plus. So how do I get this H3O plus? I need to try and figure out my HNO3, right? If I can figure out my HNO3, then I'll be able to work that out. But how do I work out my HNO3? I don't know what the HNO3 is, but what I just worked out, right? The question before, I worked out the number of moles of barium hydroxide. And the question kind of leads us, says the number of moles of barium hydroxide that's required to react with the excess HNO3. So already this question has linked HNO3 with barium hydroxide for me. So to get the HNO3, I need to then find my concentration of my barium hydroxide, right? And then with that, the concentration of the barium hydroxide, that I do have because I calculated that in the question above. And then once I've got that, I'm going to work out my HNO3. Once I've got that, I'm going to work out my pH. And then you basically work backwards from there, right? That's the step I want you guys to do in this particular case there. I want you guys to basically use that methodology to find those steps. Once you've got those steps together, then you'll be able to solve this particular problem. So let's take it from there. We worked out our barium hydroxide. That was given to us in the previous question. So we're going to use this in here, and then I'm going to work from here to there, and I'm going to work from here to there, and now I've got my pH. Let's go ahead and let's do it, right? So the barium hydroxide was given as 0.003 moles. In this reaction here, I can see that HNO3's got 2 moles to 1 mole of barium hydroxide. I need to then use my mole ratio to find the number of moles of HNO3 that was in excess, right? So let's quickly go do that. So my number of moles of HNO3 in excess, right? The mole ratio of that to my number of moles of barium hydroxide, the mole ratio was a 2:1, if I'm not mistaken. Yes, it was a 2:1. And I already know the value of my barium hydroxide. We worked that out, right? That was given to us as that 0.003. So I'm going to then basically work that one backwards and say, well, this is going to be 0.003. I need to solve for my number of moles of HNO3. I'm going to call that X. If we use our cross multiplication method, I'm going to multiply X by 1, multiply 2 by 0.003. So X in this case here is going to be 2 times 0.003. And what does that give us? That gives us the number of moles of HNO3. Remember, these are the moles in excess as 0.006 moles. Right? Okay, that's now our first step. Thank you for the ones that are posting the answers in the chat. You guys are doing phenomenally well. All right, cool. If you guys are with me thus far, please just give me a thumbs up in the chat. So remember what I said is that the question's asking for the pH of the solution after step 1. Remember step 1, we react nitric acid with our metal carbonate, right? Our nitric acid was in excess. So the excess amount of nitric acid, the amount that did not react, we take that, bring it down, and we're going to react that with barium hydroxide to form that. That is step 2. So the question is asking now, what is the pH after step 1? We need to go figure out what the pH, what the concentration of our HNO3 was, right? By doing that, I'm going to say, well, we know the number of moles of barium hydroxide, right? We need to figure out pH. So we say to figure out pH, that's negative log of H3O plus ions, the concentration. How do we get the concentration of H3O plus ions? We need our concentration of HNO3. Right? How do we get the concentration of HNO3? We're going to get the concentration of barium hydroxide, which we've already solved in the previous one. And then we're just going to work our way backwards. So we've done step 1. We know the concentration of our barium hydroxide, right? We use that now to figure out the not concentration, the number of moles. We use that now to get the number of moles of our HNO3, right? That have reacted in this particular case. So number of moles of HNO3 that have reacted is going to be basically the same as the number of moles of our H3O plus. Remember what we said in the beginning there, right? We said the fact that how are we going to find H3O plus concentration? Well, our concentration, right, or the number of moles of, sorry, let me quickly erase this. Our number of moles of H3O plus is going to be the same as the number of moles of HNO3, because that is the reason why we have the H3O plus in the first place. It's that NO3 that does that. So now we're going to use that and we're going to figure out the concentration of H3O plus, because the number of moles of those two things are going to be equal, which means we can take the answer of the number of moles of HNO3 and deduce immediately the number of moles of H3O plus, being number of moles of H3O plus is going to be 0,006 moles, right? And now I can go find the concentration of my H3O plus and plug it into my pH calculation. So the concentration of H3O plus is going to simply be number of moles over volume. So concentration of, I hope that color might be a bit too bright. Let me take a color that's a bit more visible. There, so the concentration of H3O plus is going to be equal to number of moles divided by my volume. The moles we just worked out is going to be 0,006, but what is the volume, right? The volume we need to deal with, we need to quickly go back and see what they gave us in that particular example there, right? So the question then states, as we quickly go through it, let's quickly go back and see that we had 0,198 grams of impure metal carbonate reacted with 25 cubic centimeters of a 0,4 mole per decimeter cubed solution of nitric acid. So there's our volume of nitric acid, right? That we ended up dealing with there originally. So we're going to go and use that volume, plug that volume into our equation, and then we can then solve for the concentration. So the number of moles we worked out, that's going to be 0,006. The volume of nitric acid was going to be 25 cubic centimeters. We have to convert that to decimeters cubed. So we divide 25 by 1,000. That's going to be 0,025. And then we can plug that into our calculators and then work out the concentration, right? So if we work out the concentration of H3O plus, if you plug that in your calculator, you should get an answer of 0,24 moles per decimeter cubed, right? That's what we've got there. Hope you guys are with me in the meantime. Let me just double check the chat for anything. Okay, sorry, someone is just asking there. Which step is the HNO3 in excess? So the excess HNO3 is going to be used in step 2. So we start off with the HNO3 originally, and then the one that's in excess is going to then be in step 2, right? That's very important. Step 2 is where it's going to be in excess. Cool. And then as we go down, we now got our concentration, which is 0,24 moles per decimeter cubed. We can finally answer our question, right? And now we've got this part, which is the concentration of H3O plus. We can go and solve for our pH, which is going to be negative log of that concentration. And then for our final step, let's quickly go do that. So our pH equals negative log concentration of H3O plus. That's going to be the negative log of 0,24. And then if you plug that into your calculator and do the negative log of 0,24, you should end up with an answer of 0,62. And that is the pH of the pH of the solution after step 1, right? 0,62, because we had a lot of nitric acid, which nitric acid is a strong acid. So we expect that to be a very low pH because it's going to be a strong acid. It ionizes nearly completely. So someone is asking there, is it always like that? I'm not sure what you mean, G. Maybe you can quickly type in again and finish it off. Someone also asked, what are the units? pH doesn't have units. So pH is just as it is. So remember, pH goes from 1 up to 14, no units at all. You just end up with 0,62. Okay. Hope that makes sense. If it makes sense to you guys, please give me a thumbs up. I'll quickly repeat the process that we had to follow to get here. So remember, I know it's, like I said, be ready for lots and lots of calculations, but what's important is the methodology we follow. So remember, the question says, what is the pH of the solution after step 1, right? And then someone asked a question quickly before I go through this again there, right? So we shouldn't use the titration formula for that. Definitely not. Don't use the titration formula in this particular case here. You wouldn't get marks for using the titration formula. So what you had to do here is try and figure out from your very end of step 2, work your way back to the beginning of step 2, because the beginning of step 2 is the end of step 1. And if you can find the beginning of step 2, use that concentration across, and that is how you'll figure it out, right? Okay, so a quick one there. There's another question here. Someone on Zoom said, "Sir, can you please repeat?" I'll definitely do that. Another question says, "In which step is the initial number of moles of the excess acid reacted?" Sorry, I'm trying to make sense of your question. In which step is the initial number of moles of the excess acid reacted, number of moles, and excess? So remember, if we quickly go back to the beginning, right? We have a certain number of moles of nitric acid, right? We're given this information about the nitric acid, right? That amount of nitric acid is going to be this one here. At the beginning, at step 1, we are going to react that with our metal carbonate, right? Right? And this is how much of the metal carbonate we've got, right? In that case there, once we've done that, there's a certain amount of HNO3 that remains left over. So at the end of step 1, whatever's going to remain at the end of step 1, that we're going to use here, right? And that's what, at the end of step 1, that remains, we're going to use in the second reaction. So it says again here, step 2, the excess HNO3 is then neutralized, right, with that much of the barium hydroxide solution. So then that's what we're going to do. We're going to say, well, I need to figure out what's happening here at the end of step 1, which is the same thing as the beginning of step 2. So what I've got is I've got information about this barium hydroxide, which is this here. I can then figure out how much HNO3 I needed to react with this, right? Because that will be able to give me this. This will give me then the number of, or the concentration of H3O plus ions in the solution at the end of step 1, and that will then be able to help me solve for the pH. That is the key step that I'm taking. So the step that I said, I need to figure out pH, right? So in order for me to figure out my pH, this is the equation for pH. What do I need? I need the concentration of H3O plus. I don't have the concentration of H3O plus. So how can I find it? The concentration of H3O plus, if we go back to the very, very beginning, I made mention of this thing here, where the Arrhenius theory, although it doesn't normally get asked a lot, but it's useful to know, right? That an Arrhenius acid is one that forms H3O plus ions in water. It increases the concentration of H3O plus ions in water. So my acid is what's going to then basically do that for me. So if I come back to my question, right, we say we need our pH. That pH requires concentration of H3O plus. I don't have the concentration of H3O plus, but what I can do is I can go find my acid, because my acid is going to be the thing that creates the H3O plus in water. So then to find my acid, at the end of step 1, beginning of step 2, this HNO3 is what I'm looking for. So if I can find the concentration of HNO3 or number of moles of HNO3, that will really help me in that process as well, right? But now I don't have a concentration for HNO3. How can I find that? Well, I can always use stoichiometry, because I do have information about the barium hydroxide. That was given to me, and that's what we've got here. So if I use this and use the mole ratio to find that, I now know where I was sitting at the beginning of step 2, right? At the beginning of step 2 is the same thing as at the end of step 1. So once I can do that, then I can find this, that'll help me find this, that'll help me solve for this, which will give me the answer that I'm looking for pH. And that's essentially what I then did with this particular question, right? And then what I just did there, we solved our barium hydroxide before. I took that there, and then we're going to use our mole ratio, right? It's a 1:2 in that case there. So I use that there to find the number of moles of our HNO3, right? at that point there that we basically had remaining at this point, at the end of step 1, at the beginning of step 2, which is really the point that they're asking me about, right? Because the question says the pH of the solution after step 1. At the end of step 1 is the same thing as the beginning of step 2. So if I can then figure out how much HNO3 reacted with the barium, that is going to give me what I started off with at the beginning of step 2, which is at the end of step 1. So once I've then got that, I can work at the number of moles of that. The number of moles of HNO3 is going to be equal to the number of moles of my H3O plus, right? How do I know that? Is because HNO3 is a monoprotic acid. So let's quickly go back to our theory again, to the types of acids we're dealing with. So we're looking here at a monoprotic acid. Monoprotic acids can only donate one proton, right? One H plus. If I had H2SO4, H2SO4 can donate 2 of them, right? Which means for every one H2SO4, I'll create 2 H3O pluses. But in this case, I'm only dealing with a monoprotic acid, which means it's going to be a 1-to-1 ratio of my acid to H3O plus. If it's diprotic, I'll have 2 H3O pluses. If it's triprotic, I'll have 3 H3O pluses. But in this case, I only had a monoprotic acid, which means for one of these, I'll have one of these. And then I know that the number of moles of my H3O plus will then be the same. I've got the number of moles, I can go work out the concentration. Now that I've got the concentration, I can go work out the pH using the formula. And that's the step that I need to take from there to there to there to get my final answer of pH there. Okay. Like I said, guys, today, let's just hold on as much as we can, right? As soon as we hold on as much as we can, then basically what is going to then be done there is we're going to get the answer, right? And then we'll do it step by step. Acids and bases is not a topic you're going to nail or land in one session, right? It's a topic that requires you to do lots and lots and lots of practice. Today, I just want to show you that methodology of let's put our steps together to say, I need to find this, then this, then this, then this, and then follow those steps down to your solution. So this methodology is very important. This is what I want you guys to develop in this, because the next question is going to be quite a bit more challenging than the one we just did right now, right? Don't panic, don't fret. I'll then come back and I'll repeat, and then we can even try another question later on after this one as well, right? Okay, so let's look at the next question, which is going to be, it's going to have a lot more steps. It's going to be a little bit tricky, but let's try and keep together, right, on that one. So that's going to be 7.3. You can even see it's a very long question. It's out of 8 marks, right? They want us to figure out the percentage purity of our metal carbonate in the sample. The percentage purity is 85%. They want us to identify the metal, right? We need to figure out what is that metal that we're dealing with, the metal M. So we need to quickly go back and say, whoa, slow down. What is happening in this case and how can we actually go and solve this, right? So we need to go find what is this metal M. To know what the metal M is, right? I'm going to do a little bit of a plan. Like we did before, let's look at our game plan. So to find the metal M, how do we identify an atom? So if I ask you to identify carbon, how would you identify carbon? What is a property of carbon that you can then use to identify that, oh, this is carbon? Post quickly in the chat for me. If I said you need to identify carbon out of a list of atoms, how will I identify carbon? Okay, there we go, right? Cool. Jabulani and Wakila, you guys gave me some great answers. It's the molar mass, right? So if we can find the molar mass somehow through this calculation, we can figure out what M is. So to find M, which is funny because it's going to be the same letter, we need M. So I'm going to just put MR, right? Sometimes they write it as MR, which is our relative molecular mass for substance M. So now to find the relative molecular mass of substance M, we need to figure out a couple of things. How can we figure out the relative molecular mass? If we quickly go back, right, an equation that we have that's got relative molecular mass is this equation here. Number of moles is equal to small mama over big mama, right? Capital M over small m over capital M. So if we find that M there, we can then work back and find what substance it is. So that's capital M, we can find it. What we need to know at that point, we need to know the number of moles of MCO3, or we need the mass of MCO3. right? In terms of the moles of MCO3, we don't really have a lot of that information, right? In terms of the MCO3, but we were given a mass. The mass we were given is at 0,189, right? So we've got the mass. The only thing that we need to keep in mind is we remember that we were told that it's only 85% pure, right? So when we do that calculation, the mass, that 0,1, what is it? 0,198, I think it was. Yeah. 198 grams, we need to multiply that by 80%. It's only 80% pure, right? So the other thing that we now need to figure out, we've got the mass, we need to figure out the number of moles. So how are we going to figure out the number of moles? That's got to be our next step. So to figure out the number of moles, all right, of that MCO, we need to find something else, right? I think the best bet that we're going to have there, because we figured out how much of this was in excess, right? At the beginning, and we knew how much we started off with, we can actually figure out how much HNO3 reacted, because the number of HNO3 that reacted will help us solve for this thing here using stoichiometry, right? So what I can do there is to find the number of moles of my MCO3. What I can do there is I can try and find the number of moles of HNO3 that reacted. Very important. That reacted, but remember, I know what I started off with. We already worked out what was in excess. So figuring out what was reacted is not that difficult, right? And then once we do that, we then can easily go and work out what we need to do. So figuring out what was reacted requires me to then say, finally here, the HNO3, the original minus the excess will give me what was reacted. And then I've got my steps because I know I've got the original, right? Do I have that? Yes, I've got the original. I've got the excess. So I can work out what was reacted. Once I can work out what was reacted, I can take that, use mole ratios to find the number of moles of my MCO3. Once I've got the number of moles of my MCO3, I can find the molar mass of MCO3. Once I've got the molar mass of MCO3, I can find the molar mass of just M. And then with just the molar mass of M, I now know what metal this is. So notice how this is a very long process. But now I've solved the problem for myself mentally and in plan form. When I go, all I do is do the steps from the end back to the beginning. And this is the one thing I want you guys to learn how to develop. Because if you guys are planning to get distinctions for this topic, this is what you need to be able to do, to plan how you're going to answer the question and then go back and solve that particular question. But now it's easy. We've got our plan sorted. Let's go and figure out exactly how we are going to go and do this, right? So remember, let's start with our step one. I'm going to call this our step one there, right? Once we've done our step one, we're going to do our step two. This is figuring out how much was reacted. And then our step three is finding the number of moles of the MCO and then and so on, right? So step one, sorry, let me change that color.
So
step one, hey Theo.
Rajote says repeat the step. I'm not so sure which step.
Okay, it's fine. What I'll do is I'll repeat the whole formula, right? That's going to get us the final answer. Let me quickly do that. So the question says, the percentage purity of MCO3 in the sample is 85%. Identify the metal M. So we need to go and identify what on earth this metal M is, right? This is quite a tricky question. If you can get this question right, you have no reason not to get 100% for chemistry. Okay. It is a very tricky question. Don't feel bad if it feels challenging at the moment. More and more practice is going to make it easier for yourself. So let's start at the very beginning. I'm going to start here, right? Start here on the left-hand side. So on my left-hand side, we said, how do we figure out identifying metal M? How do we identify a metal or identify any kind of atom, right? And then a couple of people gave us, so Jabulani there on TikTok, someone else, Wakile on Zoom, gave us the answer. They said, we need to find the molar mass, right? I said, fantastic. So we need to find the molar mass, because once we have the molar mass, we can identify it clearly from our periodic table. What is that metal? So how do we find the molar mass? The only thing I can think of right now, the only formula or calculation I know that's got molar mass in it is going to be calculating the number of moles. So N is equal to mass in grams divided by mass, the relative molecular mass, the molar mass. So that's the next step I need to then do, right? So to do that, what do I need? I need the mass in grams. Yes, I've got that because I was given that it's 0,18198 grams, but we need to remember something very important. We were told it was only 80% pure, right? It was only 80% pure. Let me actually write this in a color that's more easily seen. So again, the mass in grams is going to be 0,198 times 80% because it's only 80% pure, all right? So now if I find the mass and then I can find the molar mass, what I need as well is the number of moles. Now, how do I find the number of moles, right, of our MCO? The only way I can find the number of moles of our MCO, in this case here, is if I use stoichiometry, right? Remember what we did before. We went and we figured out something very critical. We figured out how many moles of our HNO3 we had at the start of step 2, meaning we figured out what was in excess, right? Now, to figure out how much reacted, we say, well, how much did I have in the beginning? So I was told I've got this much in the beginning. So I've got my original amount. I also worked out my excess amount. The original amount minus whatever was in excess means that's how much I reacted. So I can actually find how much I reacted by taking the original minus the excess. So then what I can do there is I can find the number of moles of HNO3 that reacted minus by taking the original minus the excess. Because once I've got the number of moles of HNO3, which is this one here, right, the number that reacted, I use my mole ratio to find the number of moles of M carbonate. Because then with M carbonate, once I've got the number of moles of M carbonate, which is this N over here, I can plug it into this equation, find the molar mass. Once I've got the molar mass, I can then clearly identify it from my periodic table, right? Those are the steps that I need to take in terms of this question, and then we're going to then basically solve it. So let's stick together with this problem, and I'll always remind you at every step that this is step 1, this is step 2, this is step 3, etc. Right? Okay, cool. So let's look at number 1. We need to find how much HNO3, right, reacted. So let's quickly remind ourselves. I'm going to write it here, and I'm going to try and write it out more and more every time so that we know what step we're doing. Step 1, we need to find the HNO3 that reacted, right? How do we find that? We're going to find the original amount minus the excess. Okay, that's what we need to do to find this. Now, the original amount that was given to us in the very beginning of the question. How can we find that? We can see very much up here. So it says there we reacted 25 cubic centimeters, right, of a 0,4 mole per decimeter cube nitric acid solution. So there we've got a volume and we've got a concentration. We can find the number of moles we had originally. So let's quickly find that one there. So originally, number of moles, N is equal to C times V. The concentration was given to us as 0,4 moles per decimeter cubed. The volume was given as 25 cubic centimeters. It's got to be always in cubic decimeters. So we're going to say that 25 divided by 1,000. And if I put that into my calculator, you should find that you get an answer of 0,01 moles, right? So again, the original amount is given as from the question. If we quickly go back up again, we were told there very clearly that 25 cubic centimeters of a 0,4 mole per decimeter cubed solution of nitric acid. So we just worked out what was the original amount. Now, to find what was reacted, we need to also then find what was in excess, right? But that's fine because we've already solved for what was in excess. What was in excess was solved in a previous question, right? Where we then went back here, where we found the barium hydroxide that reacted with the excess HNO3, right? And then we figured out there that the number of moles of HNO3 in excess is going to be this here. It's going to be, we did the mole ratio. So we had 0,003 barium hydroxide moles, and the mole ratio is 1 is to 2, which means we ended up with 0,006 moles of nitric acid in excess. All right, so we can quickly go put that in. I don't need to do another calculation. That was 0,006. I hope I put that correctly. Yes, 0,006, right? Moles in excess. Therefore, to find the number of moles that reacted, it's original minus excess. So then we can simply plug that one in, and we can say the number of moles of my HNO3 is going to be 0,01 minus 0,006. You can plug that into your calculator and then see what answer you guys get, just so I can keep you guys together. To someone there's asking, the volume of HNO3, did it not change in both steps? So again, in this part of the question, I don't need the volume because I'm dealing with the moles, right? So the moles, I can confirm them mole for mole. I can just do it that way, right? Okay. So if you guys then take that 0,01 minus 0,006, we can then clearly see there, you're going to end up with, thank you, Kaugelo, for your answer. We end up with 0,004 moles for our number of moles of HNO3 that reacted. Okay, so let's quickly go back and look at our plan. We just figured out the number of moles of HNO3 that reacted, right? We've got that done. Now we need to go find the number of moles of our MCO3, right? We need to find the number of moles of our MCO3. How do we find the number of moles of our MCO3? We've got to use mole ratios, right? So we've got our MCO3 and the ratio of that to my HNO3. Let's quickly go back to our step 1. So we've seen the HNO3 and MCO3. It's a 2-to-1 ratio, right? Of that, it's 2 to the HNO3 and 1 to the MCO3. What we do have, we know how much HNO3 reacted, which is going to be 0,004. The MCO3 is going to be X. We got to figure that out. Cross multiply 2 times X, 1 times that. We then know that X, 2X is equal to 0,004. And then if we divide both sides by 2, we then know that the number of moles of our MCO3 is going to be 0,004 divided by 2, which will give us 0,002 moles, right? Okay, so thank you guys for all the ones that are posting the answers there. Pulos of Khafela, thank you guys so much there. So we can clearly see now in terms of our steps, we worked out the number of original moles, excess moles, how many reacted. And now we just found out how many moles of our HCO3 we've got. So we've got this. So now we can finish off that step 3. That step 3 is figuring out the molar mass of MCO3, right? So in step 3, we're going to find the molar mass of MCO3. I didn't write up here. Should I said step 2? I need to find the number of moles of MCO3. That was step 2. So step 1, I was finding the number of moles of HNO3 that reacted. Step 2, using stoichiometric ratios, I'm going to find the number of moles of MCO3. Then step 3, I want to find the molar mass of MCO3. Remember what we said? We said we're going to use this equation here. N is equal to mass in grams divided by relative molecular mass. Remember our mass, we told our percentage purity was only at 80%, right? So when we substitute our values in here, number of moles, we're going to have 0,002 is equal to, the mass is going to be 0,198 times 80% only because it's not fully pure. And then we can solve for our relative molecular mass. So we can see there, to find a relative molecular mass, we're going to then say 0.198 times 80% divided by 0.002. And then if you plug that into your calculator, if you guys are already moving there, fantastic. You guys are doing really, really well. In that case there, when you plug that into your calculator, you should find that you then have a relative molecular mass. Sorry, my calculator is giving me issues. Give me 2 seconds. Quickly do this again. I'll try it on my phone. Sorry, someone made a note there. Sorry, it's not 80%, it's 85%. I misread that. Apologies for that. They said 85%, not 80%. Let me quickly rectify that. It's 85%, right? I think that's probably why I was getting a weird answer. 0.198 times 0.85 divided by 0.002. And then you should get around an answer very close to 84 grams per mole. Awesome. Yeah, 84.15 grams per mole. It's an answer that you should get. And then let's quickly work out 85 grams per mole has got to come from a number of things, right? So we've got MCO3. So MCO3 is going to be, we start off with M, we have carbon, and we've got oxygen times 3, right? That's got to add up to give us our 84. And then to solve for that, we have M sits there. Carbon is going to be 12. And then we've got 3, oxygen is 16. 3 times 16, that's equal to 84. And then if you solve for your M, your molar mass, you should then have 84 minus 3 times 16 minus 12. And then you guys can quickly try work it out and see what answer you get. So your 84 minus your 12 minus your 3 times 16. And then there we go. We got 24. Well done to the guys who got that there. We end up with 24 grams per mole. And then if you take 24 grams per mole and you look at your periodic table, what metal has a relative molecular mass of 24? Well done, Wakile. You were very quick with that one. Magnesium. Magnesium becomes the metal we're dealing with, right? Therefore, M equals magnesium. All right. Fantastic. Thank you very much to everyone who's putting the answers in there. Thanks, Priscilla. Thank you, Tato, for giving us the answers. Thanks, Prime on TikTok there. And thanks, Jabu, for picking up the 85%. It really did help. I might have made a mistake on my side as well. There. Awesome. So that's basically how we work through that. I'm going to quickly go back and just for one last time, show us how we then take those steps, right? So this really was a bit of a tough one. But remember what I said to you guys at the beginning of this session, guys, that you've got prelims coming up. Prelims tend to be tricky exams. They tend to be more challenging exams, right? So I want to give us questions that are going to really test how much can we really push ourselves in a question like this. So remember, for this one there, we said we're looking for the to identify the metal M, right? To identify the metal M, we need to start by doing what? Finding the molecular mass, the molar mass of metal M. To find the molar mass, there's an equation that we've got. N is equal to mass in grams over molecular mass, and that's going to be equal to number of moles. We've got the mass in grams. We don't have the molar mass, but that's what we're trying to solve. So to find the number of moles, we're going to use our mole ratios, right? And what we can do is find the number of moles of HNO3 that reacted, right? Once we've got the HNO3 that reacted, how do we find that? We say, well, take the original amount of HNO3 minus the excess. And then that's step 1, step 2, step 3, and then we can find our answer. How we did that? HNO3 that reacted is original minus the excess. The original, we were given the fact that we've got a solution that's got 25 cubic centimeters, this number here, and the concentration is 0.4 moles per decimeter cubed. That was given in the question. We can take N is equal to C times V, use that, sorry about that, use that to then work out the number of moles, which we get 0.01 moles. Then to find the number of moles in excess, we don't have to do a calculation because we solved that previously. We can just take that number as it is and use it. And then to finish off step 1, we're going to say original minus minus excess will give us reacted. So 0.01 minus 0.006 will give you 0.004. Then we've nailed step 1. Because once we've done the step 1, we need to go work out step 2, which we've done. That's this answer here, the HNO3 that's reacted. So we've nailed step 1, we've nailed step 2 all together there. Then the next one is going to be finding the number of moles of MCO3. Number of moles of MCO3. So I need to move this step 2 out because I wrote it one way when I was doing it. And then eventually, number of moles of MCO3 was essentially my step 3. But either way, let's quickly go back. So number of moles of MCO3, I take this and I'm going to then use my mole ratios to find that, right? That's going to be my step 3 or step 2. Given the fact that in our reaction, we knew that MCO3 and HNO3 had a mole ratio of 1:2, right? And we know that we've reacted 0.04 moles of HNO3, which we put there. Then we need to solve how many moles of MCO3 did we react. Cross multiply those two, you get 2x is equal to 0.004. 0.004, then you divide both sides by 2, we end up with 0.002 moles of MCO3. Now I know how many moles of MCO3. The next step is, this is step 3, I need to figure out now what is the mass, the relative molecular mass of MCO3, right? To do that, I'm going to use this equation here, where I've got the number of moles. We just worked these ones out there. We've got the mass. We were given a mass at the beginning, and we were told that our percentage purity is only at 85%. And then we're going to use that to solve for our relative molecular mass, which we then did. And then after correcting that 82 and 85, we got the right answer, which is going to be 84 grams per mole as the relative molecular mass for MCO3. Then finally, to find magnesium, we then need to quickly go and say the relative molecular mass of MCO3 consists of 1 atom of M, 1 atom of carbon, and 3 atoms of oxygen, which is going to be M plus 12 plus 3 times 16. That will add up to 84. Let's solve for M. We get 24 grams per mole. And then finally, we now know that which atom has got 24 grams per mole relative molecular mass. That's going to be magnesium. Bit of a challenging question, but we got to the end of it at the end of the day. Remember, guys, the key thing is go and practice, go and practice, go and practice. That is a very important thing. Okay, to end off the session that we're going to do now with these questions, I'm going to give you guys 2 more multiple choice questions for you guys to try, and then I'll leave a Q&A at the end for you guys to ask anything that might still be unclear, right? For those that weren't with us at the beginning of the session, remember, this is how we do our multiple choice questions, right? We have the question there. When you know the answer, post it in the chat. So in the chat, just write down an A, a B, a C, or a D. So it says, which one of the following salts, when dissolved in water, will not change the pH of water? So is it sodium carbonate? Is it our COO2Na2, right? Is it ammonium chloride? Is it sodium chloride? Which one of the following salts, when dissolved in water, will not change the pH of water? Thanks, Jabulani from TikTok, for the quick response there. Let's see anyone else. You guys still have time. I'll give you 2 minutes to work it out. Thank you to the general for their answer there on TikTok. Thanks, Tapela, for your answer there on Zoom. It's still time. It's like 1 minute and 45 seconds. Take your time, guys. Think it through and see what you guys can find. So which one will not change the pH of water? General's changed his answer from what he had before. Oh no, you didn't change your answer. Sorry, I saw something that was not correct. So we've got some more answers there. Poluso, Kimberly, Rosina's there. Rukhotso is there. Thank you so much, Tapelo. Thanks for everyone who's posting their answers. Cool. I'm going to say 45 seconds left. For those that haven't answered, please make sure you go and put your answers in. Thanks, Sane. Thanks, Wakile. Thanks, Levo. Thanks, Kitumete. Thank you guys for putting your answers in. Okay, 20 seconds left. Let's get our answers in, guys. Those of you who haven't put your answers in, remember the best way to learn in this session, let's be interactive. Let's engage, ask questions, and then you will be able to really learn a lot from that process. Okay, 10 seconds to go. All right, for those that just joined on TikTok, we've got a question on the screen. Simply give us your answer by posting either A, B, C, or D in the chat. You got 5 seconds left. 3, 2, 1. Fantastic, guys. Thank you so much for that. Let's have a look at the question together, right? And see which is the correct answer. So, which one of the following salts, when dissolved in water, will not change the pH of water? We've got Na2CO3, COO, all 2, and Na2. We've got NH4Cl, NaCl. So the key thing here is to figure out which one will not change the pH of the water, right? I'm going to do a quick little recap, right, from our notes from earlier. When doing that hydrolysis of salt solutions, right? So remember, why does it happen? So in a neutralization reaction, right, there's a product that is a salt, right? And sometimes that salt will react again with the water and it'll change the pH of the solution. Remember that information at the very beginning, right? So one that will change it is either if we end up with an acidic salt, it will change the pH of the solution, right? It'll make my pH more acidic. If we end up with a basic salt, it'll make my pH more basic. But if I end up with a neutral salt, the neutral salt will not change the pH of my solution, right? Because none of the parts will react with my water again. So let's try and see which of those. So what I'm looking for is a neutral salt, right? A salt that is going to come from a strong acid, strong base, or weak acid, weak base, right? In that case there. So let's quickly have a look at that. And then I think this even gives us our answer straight up because we can clearly see this salt here is a salt that's not going to change the thing because that's going to be the neutral salt that I'm looking for. Okay, so let's quickly go down and back to our question and see what the answer might be. Going back to our question, we can clearly see which one will not change the pH of the water. You know, little hint, hint. We already saw our answer there as answer D. But to do justice with multiple choice, I don't like to just say, this is why this one is right. I want to prove to myself, why is the other one wrong? Very important, right? So let's quickly have a look at A. Why do I say A is incorrect, right? You're going to have NaCO3. Your Na, right, comes from NaOH. That's going to be a strong base, right? That's a strong base. Your CO3 comes from carbonic acid. I think it's H2CO3, if I might be mistaken. Sorry, I'm just quickly putting this together, which is not going to be a strong acid. It's going to be quite a weak acid. So if I've got a strong base, weak acid, I'm going to have more of a basic solution. And then we're going to end up with our pH being changed. So A is not going to be the case. So we can scrap that one there. All right. And then let's quickly look at the next one. Sorry, there we go there. So COO2 and Na2. The COO2 comes from acetic acid, right? Not acetic acid, sorry, oxalic acid, right? And then the Na2 comes from our sodium hydroxide. So we've got oxalic acid, which is that COOH, all 2 like that. That's going to be a weak acid. There's a strong acid and a weak base. That's a weak acid. Our Na comes from NaOH. That's going to be a strong base. So I end up with a basic salt, and the basic salt will change the pH of my water. So that's not going to be the case. NH4Cl, the NH4 comes from ammonium hydroxide. It's going to come from NH4 OH, that's going to be a weak base. The Cl comes from HCl, that's a strong acid, which means I'm going to have an acidic salt. Acidic salt is going to change the pH of my water, not the answer. And now I've proven to myself why D is the correct one, because Na comes from NaOH, Cl comes from HCl. NaOH is going to be a strong base. HCl is going to be a strong acid. Strong and strong will give me the neutral. That neutral salt is what's not going to change the pH of my water, essentially. So we won't have conjugates coming in and reacting with the water again. So if you got the answer D, give yourselves a round of applause. I saw very few D's in there. The General gave us a D there on TikTok. Shout out to you, General, for getting that one correct. And then I didn't get any other D's. So General, you're the only one that got that correct on TikTok and on Zoom. Well done for that, man. You really did well there. Okay, and then let's quickly go look at 1.8, right? So 1.8, it says a dilute acid is titrated against potassium hydroxide solution, KOH. At the equivalence point, the pH is 7. Which one of the following combinations correctly identifies the acid and the most suitable indicator for this titration? That's our final question for the day. I'm going to give you guys 2 minutes, right? So we're looking there. A dilute acid is titrated against a potassium hydroxide solution. At the equivalence point, the pH is 7. Which of the following combinations correctly identifies the acid and the most suitable indicator for this titration? I'm going to give you guys 2 minutes. Choose A, B, C, or D. Okay, while you guys are busy with that, please remember, if you are joining us on TikTok Live and you're enjoying it, please, please, please share the live, like it. We're going to do lives daily. Sometimes we do have technical issues where we aren't able to go live, but most days we are back in the office. We're not on the road anymore, so we are able to do our lives daily. So we do our lives daily, Mondays through to Thursdays. Mondays and Wednesdays are going to be our maths days. We're doing a road to prelims, so we're going to cover maths topics, and then Tuesdays and Thursdays we do physical science in that way there. In terms of the topics that are coming up, I'll tell you guys just shortly. So for this week, yesterday's calculus lesson had to be postponed. We had a bit of a technical challenge with our team. So for this week, we didn't have a lesson yesterday. It's going to be postponed to Friday. So today's lesson is acids and bases. Then Wednesday, we're going to do mathematics. We're going to do financial maths. Thursday, we're going to be doing electric circuits. And then Friday, we're going to be doing that differential calculus lessons. Those are the lessons that are coming up. Let's quickly see what's coming in terms of the answers that are being put up there. If anyone just joined us, please remember there's a question up on screen. You've got 10 seconds left to quickly answer the question, right? I'm going to give you guys 10 more seconds. Thank you for everyone that's been putting their answers in the chat so far. And let's see how we do go with this one. 5 seconds to go. 3, 2, and 1. Fantastic, right? In terms of the answers that we get there, I see some D's, I see some C's, some A's there as well, more C's and more D's, and let's quickly try and see how that's going to go. Awesome. So the dilute acid is titrated against potassium hydroxide solution. The equivalence point in the pH is going to be 7, right? Which one of the following combinations correctly identifies the acid and the most suitable indicator for this titration? So when you're dealing with titrations, guys, let's remember, what is the aim we're looking at? To get to the end point, we need to react all of the acid with all of the base, right? And then we need to be able to identify, am I going to get an end point that's going to be basic, lower than 7, neutral, around 7, or basic more than 7, neutral around 7, or acidic lower than 7? What is the end point that I'm expecting, right? Once we figure that one out, we then can know what type of acid we're going to select and what type of indicator. So let's start with the acid. So potassium hydroxide, right? KOH is going to be one of our strong bases. Remember, I gave you a little cheat sheet to remember how to remember strong bases. Group 1 metals with a hydroxide will usually give you a strong base. Sodium, potassium, those ones. Those group 1 hydroxides are strong bases. So we need to now find, to counteract that, we need to find a strong acid, right? So our 2 options under the acid is oxalic acid, COOH, OH2, and HCl. So we know oxalic acid is not one of our strong bases, right? It's a weak base. If we quickly go back to our notes, let me scroll all the way up over there. Oxalic acid, COOH2, is one of our weak acids. HCl is the other option. That is a strong acid. So we know that in this case, we're going to need to pick HCl. So now that's the first thing we can do. I can cross out two of these options. So I know it's not A, and I know it's not B. So if you got A or B, I'm sorry for that. You'll get more chances later on in the week to correct yourselves and win back those bragging rights, because it's not going to be A or B, because that acid is not going to give me a neutral equivalence point, right? It's going to give me more of a basic one if I chose oxalic acid. So now that we know we've got C and D left, right? The next thing we need to do is look at the type of indicator we're going to use, right? So to pick the indicator, remember we've got three key indicators that we work with. The one indicator is going to be dealing more in our lower pH ranges. One is going to be a mid pH range, and one is going to be high pH range. Now, the one that we need to look at of the two, we've got phenolphthalein or phenolphthalein, however you want to pronounce it, as long as you can write it, that's the important thing. So phenolphthalein is going to be one that really identifies endpoints that are in the higher pH ranges, more basic type solutions, right? And bromothymol blue is the one that really is going to help us identify a more neutral endpoint. If we go back to our notes again, just to remind you guys, when we had a look at our indicators. So you can see there, phenolphthalein is one that really, you're looking at a pH range of 8.3 to about 10. It's a very high pH range. Bromothymol blue is the one that's between 6 and 7.6. That's going to be more in your neutral endpoint or your equivalence point. And that's very, very important. Sorry, guys, my laptop is about to die. Let me quickly plug it in before we have a bad moment in this live. Give me 2 seconds, I'm almost done. Okay, there we go. We're not going to have any unexpected load shedding of power in this particular case here. All right, so now that we've got that sorted, we can quickly go back to our question, and we saw that phenolphthalein is not going to be the one that I want to use, right? Because phenolphthalein is going to be a better indicator for high pH ranges. And in this case, I want to detect the equivalence point as a pH 7. So we know that our final answer is going to be D. And there's a lot more Ds I saw this time around. If you got D as an answer, give yourself a round of applause. I really want to appreciate you guys a lot for that, right? Someone's asking on TikTok, where can I get the notes? Gracious. So those notes that we have are normally in our exam prep guide. Normally what we do is we have those for students that are signed up to our programs, but we are busy with a plan to sell those books commercially. So it's a nice exam prep guide. That book has like all those notes that I was looking at. So it's got a nice one-page summary for every topic in maths and physical science, right? And then after that, it's going to have questions that are going to help you build your confidence. It's going to start with very easy questions and work its way up to more challenging questions. And then at the end of the book, we give you full past papers that you can then practice. So we're working on a plan to get that commercially out there. So at the moment, we don't have them sold commercially. We normally have them for learners in our programs, but we're working on that. Hopefully before the end of the year, we'll have a plan to get those sold commercially where you can just order those books from us. But thank you for showing interest there. And yeah, guys, that's the end of our session. So this is what I'm going to then do is just maybe pause here and see if there are any questions that anyone would like to ask. And then we can try and go through those questions. It's 8 o'clock. I know we are meant to wrap up and finish right now, but I'll give you the opportunity to ask any questions that you might have. If you are on Zoom, just you can maybe put a hand up or you can post in the chat. If you are on TikTok, you can just post in the chat any questions you might still have from this session. Okay, Theo, I don't know if there was questions that you might have seen while I was busy. You'll just give me a shout there.
There's nothing.
So I'm getting feedback on your side. Okay. Yeah, guys, if you have no questions and you guys are happy and you guys are sorted for the session, I really appreciate everything you guys have done. I appreciate the time that you guys have spent here with us today. Hope you guys have a really, 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 really awesome time for today. Tomorrow, again, join us. We've got a lesson on financial mathematics is another topic that some people do tend to find a little bit challenging. And again, the learning space ways, we're going to come in, we're going to make this topic really chilled, really easy for you. I do see a hand up. Poloso's got a hand up. Let me maybe just allow you to unmute and then you can ask your question. Okay, Poloso, I've given you permission to unmute. You can unmute. While you do that, Judith on TikTok is asking what time tomorrow. So Judith, tomorrow we're going to have 6 p.m. to 8 p.m. That's what time we do our lives, 2 hours per session. Okay. Poloso, I can't hear you. Maybe you can speak louder.
Setla Witimel was not able to attend since she was having problem with network. So I don't know what you could do about it.
It's just let her know to just tell her tutor. So if you have any challenges of not being able to connect, just at your school of the learners who are on our programs, please let your tutor know, and then they'll communicate with with our coordinators, and we'll figure it out that way, right? Thank you very much, Poloso, for that one. So any connectivity based issues you have, just let your tutor know, and then they'll communicate it with our coordinators and the team. So the Q&A for now is more an academic Q&A. Any questions that you still need clarification with on acids and bases? If you guys are sorted, then I think you're going to have a great rest of your evening. It was lovely spending time with you guys. Hope you guys have fun. Thank you guys so much. We'll see you all soon tomorrow for financial maths. Thank you.